So today's lecture is about inclined planes, and the classic example here for inclined planes is you have an object that is on a surface, and then you just start to lift the edge of the surface, and then at some point,
Wow.
wow, it's really hanging in there today, and it slides down. Okay, I think I left it there a little bit too long. See here, it's a little easier. Okay, so when it slides down by itself, if somebody were to ask you, why does it do that? What do you think the most common answer is?
Gravity.
Gravity. And today you're going to learn that you're not wrong, but that's kind of an oversimplification. And that when we look at what's really happening, we're going to have to use vectors to really nail down exactly what aspect of gravity is making this thing slide down the inclined plane all by itself. So we will revisit this, okay? All right, so now to the lecture.
Okay.
Very good job.
Thank you.
Student whose name I will not mention because I don't do that on video.
So name drop me right now.
Okay. Now, the situation that our inclined plane parallels is, and I'll hold this up, if we simply had a surface and we were like pushing this thing across it, what kind of problem that we've already done would we be dealing with when we were doing this to something?
Horizontal sliding.
There we go. So if when you hear horizontal sliding, you're like, I remember that. Anybody remember what the picture for the free body diagram looked like? Okay, give me the general picture, and then I'll ask for a follow-up to add to it.
It had like 4 arrows.
Okay, and then what was the general nature of just the picture to start with?
A box on a line.
It was like this with our object on a surface, and then NJ mentioned that, well, it had 4 arrows coming off of it. Hey, we're videoing.
Sorry.
Okay. What were the specific arrows?
Up and down was gravity and normal force.
Okay, so this was our FN, and what did we name this one?
FW.
FW. All right, and technically, what was the relationship between the two?
They cancel each other out.
They were equal but opposite. All right, what else did we have? And one of the things that you would have to be told to set this up right is, well, which way are we trying to move this box? We were usually trying to move it to the right, so what do we fill in?
FA on the right and FF on the left.
Okay, so this is our applied force. Whether we're pushing or pulling doesn't matter. And this is our FF. And what was the last thing that was it? Oh, I could add this. We had this equation for this. What was the one? Well, actually, we have 2 equations. What was one other equation that we had in this picture?
FF equals mu Fn.
Very good. FF equals mu times Fn. What did we call the mu?
The coefficient of friction.
Coefficient of friction. And then when we were putting the whole thing together, what was the big long equation we created because of this?
Oh, F net equals sigma, or F.
We add them all, yeah, sigma F, which means we added them all together so they looked like this. And the idea was that these two canceled, and so they, in essence, became 0. And then really whether this thing moved at a steady rate or whether it accelerated came down to a battle between these two. What's the only thing we're doing with this to create an inclined plane problem?
Making it an incline.
So we got this, and what are we doing to it?
Moving one side up.
Making it like this. So instead of having this be a horizontal surface, now this looks like that, and this thing here, that's really our ground. And usually, one of the things that they do with this is they will give you the angle that you tilt it at. Now, coming back to this here, I have been talking about frame of reference stuff. And in a two-dimensional problem like this, what are our two dimensions in terms of our frame of reference? How would we draw it in the picture?
A number line.
Okay, actually, it would end up being 2 because there would be 1 for each dimension.
Oh, great.
So it would end up looking, like a Cartesian coordinate system. And if we ever had to deal with a problem vector in this scenario, we would usually call this one the x dimension and this one the y dimension because it ties in super nicely with what you do in math. Okay. What are we going to do with this? We got to put arrows and stuff in the picture.
I don't know, but I have a question.
Okay.
Why is it slanting that way instead of the other way?
Oh, like this?
Yeah.
I'm going to say this is the traditional way they do it.
Ew.
That is weird.
You could do it the other way.
Because it's going backwards instead of forwards.
Oh, well, we will come to find out that it could be either.
Is FW perpendicular to the ground or the surface it's on?
You tell me.
I want to say the ground.
I want to.
That is correct. So that means, which way does FW point in this particular picture?
Still straight down.
Yeah. Most people would still say straight down. So that means that's our FW. And what about the others?
The same.
The normal force would still be opposite of the weight.
Okay. So would that mean you would be thinking like this?
Yes.
Okay.
I don't think that's correct.
No. But the answer to it is in its name. Why is it called the normal force? What was the normal referring to?
Oh,
When something's normal to another thing, especially lines in math, what does it mean?
perpendicular to the surface.
They are perpendicular. So the normal force is a force that is perpendicular to surface of contact.
Okay.
So which way would it point?
Perpendicular to the.
Like a little bit.
So when we tilted this, for every bit that we tilted this up, this one tilted with it.
Okay.
So this is there. What about the other two?
Parallel to the surface.
Yeah. Now here is where things are going to get can vary from problem to problem, because in our scenario, when we were doing this on a flat surface, we usually said, let's just pretend the object is moving to the right. And when we did that, when it came to our frame of reference, we had specific things for pluses and minuses. If we were moving this thing to the right, horizontally speaking, which way was positive and negative?
Right was positive, left was negative.
This was positive and this was negative. And really, in this particular, any problem that I'm aware of that involves friction, friction is always going to be a negative thing. So you could say, look, I know friction's got to be negative, so if this thing points opposite of that, it's got to be positive. We can use that when we get to our inclined plane. What about vertically?
Down,
We actually did kind of a weird thing here.
Down was positive.
Down was positive, and up was negative. Do you remember why?
If you switch your head to the side.
No.
It was like that.
And Anthony was like, if you go like this,
Go
it
like
makes
that?
sense.
Then that, yeah. It's like, look at the negative positive thing, and if you like turn your head 90 degrees, then it looks like a normal plane.
Oh, okay.
But I don't know
I get
why.
that.
Because
All right.
But it's, I know the
It-
real reason.
Go.
Because friction has to be negative, and the coefficient has to be positive, so Fn has to be
Correct.
negative.
We made this so that the signs would automatically work out the right way, keeping in mind that by definition, coefficients of friction are considered to be positive. Okay, so this becomes a little more complicated in our inclined plane picture, because we there are situations where you will be pushing this thing up an inclined plane, which would make us say, well, up the plane is positive, down is negative, but we could equally be doing it the other way. So the truth is, I can, and this is very unsatisfying for people who like rules. All I can tell you is that those two arrows are either going to be applied force or frictional force. And secondly, I can't tell you anything about plus or minus until you get a little more information on the problem. So this could be plus or minus. That means up here we would write negative or positive, because it can't both be the same, but depending on what you're doing with this object, it'll be one or the other. Okay. Frame of reference. This problem, it was the blue thing. Now, if you've never done this thing that you're going to see here, you might go, I don't know what to do. I use that, so I'll just use the same frame of reference here. And I'll say, I'm going to approach this problem like that. What is not good about our picture? Or what's going to be problematic where we're going to have a lot of work to do?
Because the arrows aren't all going up or down or
Correct.
side to side.
You remember I had a name for him?
Diagonal?
No.
Problem vectors.
A problem vector. A problem vector is one that does not fit perfectly into your dimensions. But if you have a problem vector, what is it that you do to it to make it not a problem vector?
Resolve it.
You resolve it. And then once you resolve it, then you have pieces that are in the two dimensions, and then you can start to process it mathematically. What could we do with this to reduce the number of problem vectors we have?
Turn it that way.
We could say, why don't I just rotate it with the inclined plane? Now, and this is where some people go, you can do that? The answer is, yeah. But I'm going to change something about this, because most people, if we say, let's talk about X and Y, they're like, it's already skewed, that doesn't work. So we actually use two different terminologies for the two dimensions here. What's the geometric relationship between this particular dimension and the plane of the inclined plane? They are parallel. So this dimension is referred to as the parallel dimension, which would make what for the other dimension?
Perpendicular.
Perpendicular. All right? Okay, so we're making progress, because now, since we've done this thing with our frame of reference, do we still have problem vectors?
Yes.
We do.
FW.
How many?
1.
1 instead of 3. Okay? So, we still have a problem vector. Which one is it?
FW.
It's FW. So that means we have to do what to it?
Resolve.
Resolve it. Can somebody come draw me what it's going to resolve like now that we have our frame of reference established? Okay. We'll see how this goes. I'm going to say, first one didn't go, it was like half right. The last two people have done okay.
I guess like
Okay?
it's kind of bad. Like that.
Okay, very good. Now, I'm going to do this, I'm going to say the mirror image of this, because this is how you'll usually see it in textbooks.
Yeah.
Okay? Same thing, but this is, I'm going to say, the more traditional look to what you do. And these have names. We could do FW and then do subscripts, but usually, since it's the only one that you're resolving, they just refer to it as F something. This is where we go to dimensions. Which dimension is this one in that we established over in our frame of reference?
X.
We don't call it X here.
Parallel.
Parallel. So we just call that F parallel. Okay, if you ever, and what's the other one going to be called?
Perpendicular.
F perpendicular. If you ever talk about F parallel or F perpendicular and someone goes, I know what you're talking about, just about the only place I've ever heard it. Okay? Now, I'm going to come back to this. If we were to apply this net force concept here before we did the resolving, how many arrows did we have in there before we did the resolving?
4.
We had 4. Any different from these 4? No. So technically, it would be exactly the same thing. Now, from the picture, we learn, okay, I got a problem with one of them, which was the FW. So we resolved it. So when we do that, see if you guys get this. How many vectors are going to be in this next math expression? Where I can really do some math with it.
5.
5. And how is it going to be different from this one? And I'll say you can color code it for me if you want. Will I still have FF?
Yes.
Yeah.
Still FA?
Yep.
Still FW? What will I have instead?
F parallel and F perpendicular.
And what am I doing with them?
You're hypotenusing it. Pythagorean.
Remember, when we
Oh.
did this,
Oh.
the idea is that these two add up to the black one. So if I'm getting rid of FW, what replaces it is
I was looking for the right term.
that.
Oh.
Because those two are the same thing as the black one. So you don't put FW and F parallel and perpendicular into the same thing because it would be redundant. And then we have that. Okay? Now this is mathematically useful because everything here is either in one dimension or the other. So that these first 3 are all in the parallel dimension. So if I can put numbers on them, I can actually just add them together. And these last 2 are both in the perpendicular dimension, so that means I could actually add them together. Now, one thing about these 2 perpendicular ones. How did we deal with them when we were here? What was nice about them?
Get canceled out.
They canceled out. Here, same thing. They are equal but opposite to each other. If it was not true, what would be happening to this as it moved up or down the inclined plane?
It would be floating.
Oh.
It would either be floating off of it or sinking down into it. So, in this one, we said Fn is the opposite of Fw. We still have that concept in play here, but not with Fw as a whole, just with F perpendicular. And this equation here, I think it was Johnny remembered, that still works here. So we have Ff equals mu times Fn, but what's different this time is our Fn is the F perpendicular in this particular triangle. Okay, we're making progress. Now, we got to figure out how to do math with this. Now, I mentioned earlier, they usually give you the angle. The other thing that they will usually give you, and you can work without this, but you got to do it more kind of conceptually, they give you the mass. So if you have the mass, what thing can you calculate up here immediately?
FW.
FW, because what's the equation?
G. Let's go.
Okay, so you could calculate that. So in this triangle, which side do you have then?
The hypotenuse.
The hypotenuse. So we want to figure out the legs. How do you do that?
Pythagorean.
No,
You use the angle.
you need an angle. Anybody see where we can get an angle? Where?
There's one right
There,
there.
you can get one there because it's 90 minus theta.
This?
Yes.
Okay. You're close.
What? Oh, it's not 90 minus theta.
Okay, hold on. I'm going to name this one
That one.
gamma.
That
Okay.
one's 90 minus theta.
Okay, so hold on a second.
Oh, it's theta.
In the picture, this is a right angle. So we have a right angle down here, which means that theta plus our gamma here would have to equal 90 degrees. But in our picture, because we have parallel and perpendicular dimensions, this is also a right angle. And that means that our unknown angle plus our gamma also equals 90 degrees. And that means what about our theta and our question mark?
They're the same.
They are the same. Do you know the technical name for this?
The transitive property or something.
Eh.
Syllogism or something.
Well, they have a geometry specific one for this.
The law of syllogism. Or
What does it start with?
the,
Does it start with?
the
It's a
transitive
C word.
property.
I know a few of those.
I swear it's the law of syllogism or the transitive property.
Well, mathematically that might come into play, but
Complementary.
the key thing is that this guy right here, if you added it with these two different angles, you know, as separate things, what did you always get?
180. Wait, what, if you added,
No. If you added this one and this one, what did you get?
Oh, 90.
And if you added this one and this one, what did you get?
90.
So,
Complementary.
what?
Complementary.
Complementary, not supplementary.
You said that a lot.
So they have a principle of I don't know if it's complementary angles.
No.
If you have two angles that are complements of the same third angle, that can only happen if the first two angles are the same.
My favorite was supplementary.
And that same thing happens if the relationship is 180 degrees, but they don't talk about them being complementary, they talk about them being supplementary. Okay, so we're making progress. Because we said earlier, what do we want? What do we need to find in here?
The F2 or parallel.
Parallel. It looks like
F parallel and
F
F perpendicular. And we said, well, I got the hypotenuse of that triangle, but I need an angle. Now you got it. So what are you going to use?
Oh, wait, that actually makes sense.
Okay, for which one?
For F parallel.
Okay, so we could use the sine of theta equals what over what in that triangle?
Equals F parallel over FW.
So if we want to solve, I'm going to put this over here. Just for F parallel, we rearrange it
Alright, well,
and you get that expression. And if you're going for F perpendicular, you use cosine. So if you rearrange that, you get F perpendicular equals FW times cosine theta. Now I do want to point out one thing. You know, as much as I'd love to say, just memorize. Don't take a picture yet. I'm not done.
why did I write
My God.
Sometimes you erase things that are important.
Yeah, well,
Oh,
he's gonna
jeez.
tell us
No.
what he's voting first.
See, I'm going to erase this, but this is not important because you got the final product over there.
Ugh, you should
Man.
take him out for that, like, for real.
No, I have students doing that. I'm like, I'm halfway done, and they're like taking a picture. I'm like, what the hell are you
Or
doing
he
that
could literally
for?
just write it in his
In addition, look what I'm doing. I'm freaking videoing this thing.
Anthony, look at my notebook
Don't change.
where it has notes in it. Oh, you
Oh.
doing that.
That is also an option.
Yeah.
Okay, so getting back to this. What dimension, when we were up here, was the parallel one?
Parallel dimension.
Horizontal.
Which is our x dimension.
Oh.
When I had you go for x dimension stuff when you were resolving vectors, what was the trig function you used?
Oh. Cosine.
Cosine. What did you use this time for that
Sign.
sign? So this is why I tell, as much as I would love to say, God, well, I can just make rules, just follow the rules. If you know the picture tells you what to do. That's why anytime you guys don't put graphic stuff into your work, I always find that lacking. Because when you say, oh, I just do this because it makes sense, there's a picture that usually goes with that to make sense of it. So that's why when you don't show the picture, I'm usually going, yeah, do you really know this? Or are you just, like memorizing a math equation? Okay, what else do we have? I think this is pretty much everything about. I do have one other thing to add that is cool. But as far as, remember when we did this and I said, everything you need is right here every time you do one of these problems? I'm going to say the same thing here about inclined plane problems. Now, can this get more complicated? Yes. But this is the core of it. Now we have to talk signs.
Uh-oh.
Uh-oh.
Perpendicular. Which way is positive and negative?
Negative is up and sideways.
Okay, so I'm gonna do this here. Negative is there, positive is there, so it kind of tracks like what we did here. What's really complicated about this? It depends. Now, this gets even more complicated, and I'm gonna see if you figure this out. Let's say we are pushing this up the inclined plane. If we are doing that, what sign goes with up the plane?
Positive.
Positive,
On the
which makes down the plane
Negative.
negative, and we need one more.
There's only two.
Is there only two?
Sign.
What dimension are we in?
Parallel.
Parallel.
How many arrows do we have in the parallel dimension?
4, 2, 3, 3, 3.
Somewhere in there is the right answer.
Is it not 3?
Where are they?
And the other one. And
They're all labeled.
the F, A, F, F.
Okay.
F parallel.
And this one here. What sign does this one have?
Oh, I thought you meant like positive or negative.
Oh, no.
That
What
one?
sign does this one have for this scenario?
Positive. Negative.
Which way does it point in the picture? Up or
No.
down the plane?
Down.
Down.
Therefore it is
Negative.
negative.
Okay.
When we're pushing it up the plane. But let's say we're using the plane to push something down. What happens to these two?
They switch.
They
keys.
switch. But that one's still negative.
No.
What is it?
Positive.
It's positive. But did it change direction?
Oh, yeah. Okay.
No.
It still points down the inclined plane. But depending on what you're doing with the object, down the inclined plane could be positive or negative. So the idea is that F parallel always points down. But when you say, well, is it positive or negative? That's when you would say, well, it depends what we're doing with the object.
Is that just for the sake of math, or is there a scientific reason with this?
I'm going to say it's the mathematical thing so that we can combine things properly.
Right. Okay.
So if you don't catch something like this, you're adding something when you should be subtracting it, or vice versa, so you end up getting off with your values.
Okay.
Okay? So that is something tricky about F parallel, because it never changes its direction, but whether it's positive or negative can vary. All right. So now, where did my thing go? Oh, it's right here. Okay.
Okay.
Remember when we did this and we said, at some point that happens? And when we said, okay, what makes it happen? The quick answer is gravity. Why is that correct but not the best answer now that you know all this?
Because it's more weight. I don't know.
It's also the normal force.
There's actually one thing up in this picture that if you said that, like, why does this do this, that I would say, okay, you've gotten to the core of it.
F
F parallel is what makes this slide down. Now, where does
Yeah.
where does F parallel come from?
From
Gravity.
It's part of FW. And where does FW come from?
Gravity.
Gravity. So when someone says gravity, it's like, okay, well, you're kind of right, but you're not very completely right. So if you ever have to do an inclined plane explanation, you could be so irritating. Bust all this out. Now I got, yes.
Does the normal force have a parallel vector?
No. Last period somebody wanted to do that, like they wanted to like do something like this.
Yeah.
Because we did this over here,
Right.
this is perfectly within one of the dimensions, so we don't break it down at all.
Okay.
Now I will say there are some scenarios that involve circular motion where you do play that game, but that's not going to come into play here.
Okay.
Now I got one other thing to finish up with here. You have something on a surface and you like tilt it and it doesn't move. You're like, damn, I want this thing to move. What do?
Tilt it more.
You tilt it more, and if it doesn't move,
More.
you tilt it more, and eventually it will do that. Anybody explain based on this picture why that happens? Okay, Anthony.
Because like the friction arrow is longer than the FN or the F parallel, not FN. Or like
Well, okay. Let me draw a picture, and then we'll go there. Okay. If it's kind of shallow, doesn't move, so you end up saying, "Hey, more." So we'll go super extreme. So here's the object here. Let me draw this here. Now, if I'm going to draw FW, and this is the same object, even though I'm at different angles, what's one restriction I have in my picture? If I'm being very meticulous.
FW is always the same direction.
It's the same direction, but even more than that.
the same magnitude.
It would be the same magnitude, so when I draw this, what do I have to try and be careful of?
Making FW the same length.
Same length. So it doesn't matter what length I make it, but once I make it on that one, I think I'm pretty close there. So this is my FW. All right? Now, so if someone says, oh, you did more with gravity. We didn't, because FW is the same for both of these. But we're going to resolve it. Okay? So, how does this explain it?
The F
As you're tilting that thing up and up, higher and higher, what's happening?
F
Perpendicular
perpendicular
Parallel
shrinks.
is
The
getting
parallel
more
gets longer.
F parallel's getting longer, and most people will go there and just say, well, F parallel's getting bigger. Now this is where you brought up FF. If FF is bigger than this F parallel, will it move?
No.
No. But at some point, the F, now this is going to be super cool. The F parallel gets bigger. So most people go there and say, see, F parallel is getting bigger. That's why it eventually slides down. So far, so good. But there's something else.
It's because F perpendicular is getting smaller, which means FN is smaller,
Which means,
FF is bigger.
exactly.
Smaller.
Smaller.
Not bigger.
So there's two things happening. And this goes back to the projectile motion. Remember when we said you have a speed that you can like launch something at? If you keep going higher and higher, one component gets bigger, but at the expense of the other. That's the same thing here because FW is exactly the same in both of these pictures. So as you are tilting your inclined plane up, you are increasing the size of F parallel, but that is coming at the expense of F perpendicular, which is not really a bad thing because if F perpendicular gets smaller, that means Fn gets smaller, and Fn is connected to how much friction you have. So when Anthony mentioned the idea of how long is the arrow for friction, it's also getting smaller as you tilt this thing at a bigger angle. So when someone really says, hey, when I get it high enough, why does it actually end up sliding? If you want the complete answer, you actually got to include both of them. I'm increasing the force in the direction I want it to slide, but I am also decreasing the friction that is holding it in place. So if someone did a calculation here and said, I have 40 newtons of friction here, how high do I need to move this thing before it'll slide on its own? If they use 40 newtons, they will end up discovering, I found the angle was 37 degrees. It'll start to slide before 37 degrees because since they're increasing the angle, the amount of friction that's holding it in place will go down from that 40 newtons in this particular scenario. That is some cool crap. When you see how everything is like interconnected with that, that's some good stuff. Okay, so the idea is tomorrow, there are only 4 problems with inclined planes on the problem set. I'm going to give you all 4 of them tomorrow. I will target the 2 that are, the good starter ones. I will tell you one of the coolest. I could bust this one out. My brother took a physics class when he was in college, and he sent me a couple of his tests.
She said his brother.
Whoa, whoa!
Oh.
It's actually a double inclined plane with 2 different masses, and you have to figure out, 1, does it even move? 2, if it moves, what direction? And then 3, if it moves in that direction, what is its acceleration as it moves? And it's like this on both sides. Awesome problem.
Crazy.
But the thing is, if you get how the pieces fit together, it's not crazy. Okay, that's it for today.